Jai Hind everyone. I am Shruti Jain, Assistant Professor, MC Department, Ajay Kumar Garg Engineering College, Ghaziabad. The topic that I am going to discuss today is the K-maps that is covered under the Boolean algebra, and the subject in which this K-map is the discrete map with the subject code BMC 101. The target students are MCA first year first semester students. So let's understand, whenever we are making a K-map, what are the terms that we usually use whenever we are working on the Boolean algebra or solving the K-maps. So the first thing that we have is the min term. Now min term is basically a Boolean variable, which is like, if I talk about a literal, it is a Boolean variable or its complement. And if I talk about a min term is a Boolean variable which is of the form x1, x2, xn, the number of variables that we need when we are working on any of the Boolean algebra or the min term. And it is a Boolean product. The Boolean product becomes this y1, y2, yn. Like, we have a combination of different variables x1, x2, xn, like this. And then we have the min term as a Boolean product, which is y1, y2, yn, where yi is xi or yi is xi complement. That means, if I talk about this y, that could be a combination of x, x1 complement, x2, x3, x4 complement, like this. So y is a combination of the complement and the variable itself, the product of the variable and its complement. So a min term is a product of n literals, where one literal for each variable. That one variable can be a complement or a normal variable. So a min term has a value 1 for one and only one combination of values of its variables. More precisely, if I talk about the min term is 1 if and only if each yi is 1, and this occurs if and only if xi is equal to 1. If xi is equal to 0, in that case we get yi as xi complement. So only when the value of xi is 1, we have yi equal to xi, and when we have xi equals to 0, then we have this thing, the complement. So complement represents the value of the variable as 0, and the normal variable xi represents the value of y is equal to xi represents that the value of xi is 1. So if I talk about a question where we need to find out the min term which is equal to 1 in the cases where x1 is equal to x3 equal to 0, that is one thing, and x2, x4, x5 is equal to 1. So wherever we have the value 1, we'll take the variables as it is. So we have x2 here, x4 here, and x5 here as 1. Now the rest of the variables, the value of these variables is 0. That means we are talking about their complement. So that is represented by x1 complement, x3 complement, like this. The complement can be written in this manner, or the complement can also be written in this manner with a dash sign just adjacent to the variable at the top in the power part. The next thing that comes is the DNF form, or we call it as a complete SOP, or the canonical form, or the complete disjunctive normal form. So when we are talking about the DNF or the SOP, so this SOP is basically the sum of the product. Now when we are talking about the product, we are talking about the min terms, because min terms is the product of the Boolean literals. When we add all those products together, we get a DNF form or the SOP form, the sum of the product form. For example, we have this xyz, this is one min term, xyz complement is another min term, xy complement z complement is another min term. The sum of all these min terms give us a function or an expression. So a Boolean expression E is said to sum of the product expression if E is a sum of the product expression where each P involves all the n variables. That is very important. If I just write it as f x comma y comma z and I say that E is equal to xy plus yz dash, then this will not be in the SOP form. We need to have all the minterms in all the minterms containing all the variables together. If any of the variable is missing, we need to introduce that variable into that expression. Only then it will be considered as a proper SOP form. So a DNF in n variable contains 2 to the power n terms is known as the complete DNF form. For example, if I talk about this, we have 3 variables. That means 2 to the power 3 terms will be there. 2 to the power 3 terms means 8. We need to have different combinations of it. So we have these 8 terms that are there in the complete DNF form. Now it is not necessary every time that you will have all the minterms in all the expressions. How do we calculate the minterms? We have A, B, C as a variables over here. Now these A, B, C variables will have different combinations. So we have 2 to the power n combinations over here again, where ABC is either 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, etc. So these are the different variables or the types. How do we represent each one of them? This 0, 0, 0 is A complement, B complement, C complement. Because wherever the value of variable is 0, in that case we consider it as its complement. This would be written as A complement, B complement, C. That is this 0, 0, 1. A complement, B complement, C. A complement, B, C complement, and so on. Now, whenever we are finding out the SOP form, we have certain values for F and F, for F. That means this F says wherever we have the value as 1, because it is a Boolean algebra, again it will have either the 0 and the 1 value. So wherever the value of F is 1, we'll consider them as the sum of the minterms. So this is 1, which is A complement, B complement, C, that is this. The value of F is 1 over here, that is A complement, B, C, that is this. This is again 1, A, B complement, C. Then this is A, B, C complement, and the last one is A, B, C. So when we add up all of them, we get a minterm or the SOP form. Similarly, we have another function here where we again have the 3 ones. So we'll have 3 terms over here. The first one would be A complement, B complement, C complement. The other one would be A complement, B, C complement. Then we have A, B complement, C complement. So this again becomes the SOP form. If we can also denote it in this manner. We always say that, suppose these are some of the terms, minterms. So we'll say this is M0, this is M1, this is M2, M3, M4, M5, 6 and 7. We can denote all these terms as in this form where we have sigma M is equal to 1, 3, 5, 6 and 7. This is another way of representing your canonical form. So the canonical form can either be represented in this manner or the canonical form can also be written in this manner. Max terms is just the opposite of the minterms. In the minterms, we are considering the product part. In the max terms, we will be considering the sum of them. So Boolean expression in k variables x1, x2 to xk is called max term if it is of the form y1 plus y2 plus y3 till yk. Here again we have an opposite part. The value would be 1 only when yi is equal to x complement. It is the opposite. Similarly, yi is equal to xi only when the value of xi is 0. So this is the opposite part. That is, if we talk about the max terms over here. So max terms is an addition. So we'll have A, B, C like this as a literals because 0 is considered for the normal and 1 is considered for the complement. So this becomes A plus B plus C, which is written as M0. This is A plus B plus C complement, that is M1, and so on. Again, coming to the function part, here when we were talking about the function, we were considering the values where the value was 1. But when we are talking about the max terms, we will be considering only those values of the function f wherever we have the value as 0. So as we have discussed just now, wherever the value of f is 0, we will be considering them as the max terms or the product of the sum. This is known as POS or the canonical normal form. This one was the SOP. The previous one that we were talking about was the SOP, sum of the products. Now here we are talking about the product of the sum. So sum is the max term. The product of them becomes the POS. Again, we need to have all the literals, all the variables in each and every max term. So this can be represented in this format where we are considering the f as 0 over here, 3 terms, A plus B plus C, this is 1. Then we have A plus B complement plus C, this is the second one. Then the third one is A complement plus B plus C, so we have this as the max term. In order to solve these, we use the K-maps. These Boolean algebra help us to simplify the expressions and the circuit. So the K-map is a graphical technique for simplifying a Boolean expression either into the minimal SOP or into the minimal POS form. How do we work on it? We have this as a truth table where we were talking about for 2 of the variables. We are currently working on the minterms. So this 0, 0, 0, 1, 1, 0, 1, 1 can be represented in the K-map as, we have this as a K-map where, because we have only 4 combinations for 2 of the variables, we have x and y written over here. So this is 0, this is 1, this is 0, this is 1, this is for x complement, this is for x, this is y complement and y. Now the combination of these will give us the K-map. Like this is x complement, y complement, so here we'll get x complement, y complement as the answer. This would be x complement y, this would be xy complement, and this would be xy. So this is how a K-map is formed in the graphical format. 3 variable K-map, if we talk about, we have a combination of 8 elements. Now that K-map can also be drawn as like this. We have 8, so we have x as one side, 2 variables on other side, 0, 1. Here we'll have 0, 0, 0, 1, 1, 0 and 1, 1. So the combination or the minterms that we'll have would be M0, M1, M2, M3, M4, M5, M6 and M7. So this is how the representation of K-map comes when we are talking about a 3 variable K-map. When we are doing it from the truth table, this is how we do it. We have 0, 0, 0, that is M0. Now at M0, the value of fxyz is 0. So we'll write 0 at M0. At M1, we have 1. M1 is this representation. So we'll write 1 over here. At M2, we have the value of f as 0. M2 is a representation over here. So we'll write 0 over here. So this is how the K-maps are designed when we are working on, we are taking the data from the truth table or we are directly taking it from the minterms. Now, how do we find out the minimal sum of the product in this case? What we do, we try to combine these ones all together. We try to form the maximum, we try to form a combination of the maximum values that can be taken up when we are solving these, the product of the sum. For example, we have like when we are grouping the minterms together, we need to make the rectangles around the groups of 1s, 2, 4s or 8 ones. All of the ones in the map should be included in at least one rectangle. We do not include any of the zeros. Each group corresponds to one product term. So this group will correspond to one product term. This group will correspond to one product term. Coming back to this, now suppose we have made the groups like this over here. The grouping is basically 1, 1, that is x complement y complement z. As we have seen, this is m0, m1, m2, m3. This is m4, m5, m6 and m7. So the combination of these two will give us one term. That term would be the common of the literals between the two. The two common literals over here are y complement z over here. So the actual answer will contain y complement z over here. If we talk about these two, here we have the common terms as x, y in both of them, the common literals. So the final output will have x, y as this. Because this is the sum of the product, so these two terms will be combined together by a sum. So this is the minimal SOP form for this given K-map. We'll see how to solve. We'll do one example when we'll be solving this. The next one, the rules that says that make as few rectangles as possible so that we have the number of products as minimal. Make each rectangle as large as possible to minimize the number of literals. And then rectangles can be overlapped if that makes them larger. This is an example where we have this as the expression given to us, that is m1 plus m2, m5 plus m6 plus m7. So when we have m1, m5, m6, m7, m1 will put 1 over here at all the places, and then we have already done the solution of this question over here. So this was the solution that we talked about here. Now here the rectangles cannot be made more than combining the two ones together. But we would be seeing some of the examples where we'll have more of them together. The 4 variable K-map, the values increase. We have a box of 16 cells where we have 0, 0, 0, 1, 1, 0, 1, 1 for 2 of the variables over here and for 2 of the variables over here. So here the rectangle groups could be of 1, 2, 4, 8 or 16 minterms. We can wrap all around the 4 sides, like this wrapping is also possible. The wrapping of the corners is also possible, like this. And the biggest part that we can consider is this whole together, when we have all the terms all together. So the representation of 4 variable K-map is like this: m0, m1, m2, m3. M4, M5, M6, M7. Then we'll come back to this M8, M9, M10, M11, 12, 13, 14 and 15. Let's see how do we solve this. Suppose this is a question given to us where we have M0, M2, M5, M8, M10 and M13. We'll put 1 at all these places. These are already highlighted over here. So we'll put 1 at all these places and we get the combination over here like this. So when we get a combination, now if we look over here, we have 1 at the corner side. So this can be combined all together in order to get a combination of 4 ones together in a square. So we'll get one term from here and one term will be obtained from here. So when we obtain this term, what do we get? From here, we have W complement x complement y z complement and W complement x complement y complement z complement. Again, we'll find out the common literals from here. The common literals would be W complement, that is 1, x complement, that is the other one, and z complement, that is the next one. So from this, we get W complement, x complement, z complement. Sorry. This is from these two. Now, when we combine these two, we'll not include this W. So, we'll not have this W over here. We'll only be left with x complement and z complement because we are finding out the commons in all these 4 terms. The common part from here, W and W complement will not be considered. Rest all are common. So, we'll have plus x, y complement, z. So, this is the solution of or the simplification of this M0, M2, M5, M8, M10 and M13. This can also be written as F. You can get the question as sigma of 0, 2, 5, 8, 10 and 13. Either you get the question like this, or you can get the question like this. Whenever you get the questions of this sort, we'll be forming the K-map like this. The first step would be forming the K-map like this, where you will be entering the ones at all the places wherever we have these values given to us. So we have done over here. Now we'll be grouping the ones as much as possible so that the maximum ones can come into one group. The more the ones in a group, the simplified version will get. So this is the simplified version for the corner ones, because the corner ones include 4. So we'll get x complement z complement by taking the common literals in all the 4. Then we have a pair over here where we have only 2 ones grouped all together. So these 2 ones grouped all together will give us a combination like this. So this is the simplified sum of the product. So that is all for today. In the next class, we'll be in the next session, we would be either talking about the solving of the POS form, because we did today the SOP form, the minimal SOP form. In the next session or in the next video, we'll be covering up the POS form of the same. That's all for today.